Okay, for this problem we have this autonomous differential equation, y prime is equal to y minus y squared. We're going to characterize the equilibrium points and draw sample solutions of this differential equation. And then after that we're going to find the general solution of this differential equation. Okay, so for starters we can write this as y prime is equal to y times 1 minus y. So we clearly have the two equilibrium points of y equals 0 and y equals 1. So the first thing we can do to characterize the equilibrium points is to draw a sign chart, 0 and 1. If y equals 0, then we get 0 clearly. It is negative below 0, and it is a positive above 0. 1 minus y is 0 at 1. Below 1, this is positive, and above 1, we have negative. So multiplying negative times positive is negative. Positive times positive is positive. Then positive times negative is negative. And so therefore, to the left or below 0, the solutions are decreasing. Above 0, the solutions are increasing. And above 1, the solutions are decreasing. So clearly, this 1 is going to be a stable equilibrium. The arrows are pointing toward 1, but both arrows are pointing away from 0, so this one will be unstable. Okay, so that's one way of characterizing the equilibrium points. The second way is to take a look at the right-hand side. F of y is equal to y minus y squared, and just simply take the derivative with respect to y. We get 1 minus 2y. Okay, now let's plug in the equilibrium points. F prime of 0 is equal to 1. The numerical value is not important. The important thing is that's greater than 0. So that means that y is equal to 0 is an unstable equilibrium. And if I plug in the other equilibrium point 1, we get 1 minus 2 is negative 1. That is negative. And so the other one is a stable equilibrium. All right, now finally, before I start sketching the solution, I can use this derivative to figure out the points of inflection of the sample solutions. So f prime of y is equal to 1 minus 2y. If I set this equal to 0, that gives me y equals 1/2. And so this will be points of inflection of sample solutions. All right, so with that, let's start sketching. So there's 0, nice and perfectly horizontal. Let's put 1 up here. And I found that 1/2 was a point of inflection. So let me put that in very light red. Just as a reminder that when I draw my sample solutions, they have to change concavity when they pass that red line. Okay, below 0, we go away from 0, because 0 is unstable. Above 0, it's going to go away from 0, but get closer to 1. So that means I'm going to go up, cross this red line, I change concavity, so to now approach 1. So up, change concavity here, and then approach 1. Up, change concavity there, and then get closer to 1. So these are the sample solutions of this curve. And then finally above 1, there's no points of inflection, so they just simply get closer and closer to 1 coming from above. So we see that 1 is a stable equilibrium, and that 0 is an unstable equilibrium. Okay, so that's what the sample solutions look like. Now let's actually solve the thing. Okay, so this problem I've asked you to do a little bit more, which is to actually find the general solution. So y prime is equal to y minus y squared. So that's dy dt. Okay, this is a separable differential equation. I can divide dy over y times 1 minus y equals dt and integrate both sides. Okay, now when I divide, I might lose solutions, so let's not forget about that. Also, To do this integral, I now need to use partial fractions. So let me do a little bit of scratch work over here on the side. 1 over y times 1 minus y. The partial fraction decomposition will be a over y plus b over 1 minus y. So clear out the denominator. I get 1 is equal to a times 1 minus y plus b times y. And now I can substitute values of y actually to solve for a and b. If I plug in y equals 0, I get 1 is equal to a times 1 plus b times 0. So that means that a is equal to 1. If I plug in 1, I get 1 is equal to a times 0, plugging in 1, plus b times 1. So that means that b is equal to 1. So 1's here, so I can have integral 1 over y plus 1 over 1 minus y dy is equal to integral of dt. So taking the integral, we get natural log of absolute value of y plus natural log, actually it's going to be minus natural log of 1 minus y is equal to t plus c. Okay, so let's combine these two natural logs. Natural log of y over 1 minus y is equal to t plus c. So that absolute value of 1 minus y will be equal to e to the t plus c. All right, now that's equal to, one more thing. So that gets y over 1 minus y is equal to plus or minus e to the constant times e to the t using the laws of exponents. So if I get rid of the absolute values, I put a plus or minus over here. Also, I use the law of exponents to split this up. Plus or minus e to an arbitrary constant is an arbitrary constant, so c times e to the t. Okay, now I'm trying to solve for y, so let's multiply up and then get all the y's on one side and everything else on the other side. So c e to the t, 1 minus y. So multiplying out, we get c e to the t minus c times y e to the t. Let's get all the y's on one side. Y plus cy e to the t is equal to c times e to the t. I can factor y out. And then divide down, so y is equal to c e to the t over 1 plus c e to the t. Okay, now I can simplify this a little bit to make this a little bit more easier to look at. Let's multiply top and bottom by 1 over c e to the t. 1 over c e to the t. Or either minus t, I apologize. So here c's cancel, and then e to the t times e to the minus t is 1. Likewise, here c's cancel, e to the t times e to the minus t is 1. Then the second part is 1 times this, so 1 over c e to the minus t. Okay, so I have 1 over an arbitrary constant, which becomes an arbitrary constant. So 1 over 1 plus c e to the minus t. So there is my solution by integration. Okay, lastly, to get our other solutions, remember that we divided on this very first step. So there's two other solutions. Y is identically equal to 0. Y is identically equal to 1 because of the division here. Now, do I recover those? If c is equal to 0, I get 1 over 1. So there's no need to write that out separately. That equilibrium solution actually happens to be handled here. However, the other solution is not. So I have to write that out as a special case that this is my general solution, or y is identically equal to 0. And so those are my two possible solutions, the forms of the two solutions the two forms of solutions, what I want to say, of the solution, either this constant or something that looks like this. And I encourage you to actually plug this into your calculator. It's probably like 2 or 3. Plug this into your calculator and actually see if the graph of this function actually does match the pictures that you see here.